Hello there guys, welcome back to another video. In this video, we will learn how to solve binary classification problem using PyTorch, and we'll be using neural network architecture. So first of all, let us understand what is binary classification. So binary classification is a classification in machine learning which goal is to categorize data into one of two mutually exclusive classes or categories. So what binary classification means is that there will be two classes and you need to pass data to your model, and your model should be able to tell whether it belongs to class A or class B. So if we go on to the image, you can see there are two classes. One is gender 1 and another is gender 2. So we need to build a model that is capable of separating these two gender. That's what we want to build today. But we will be using PyTorch and we'll be utilizing neural network architecture. So let's look at how neural network architecture looks. This is the basic architecture of neural network. This is the input layer where we'll feed data to our network, and these are the hidden layers. In the hidden layers, there will occur some computations, and finally our model will output something like if it belongs to class A or class B. Here is another good example. So this is the input layer. Hidden layer performs some calculation, and then the output layer will tell if it belongs to class A or class B, whether it is burger or pizza, whether it is red or blue, something that separates class A from class B. So the data set that we will be going to be utilizing in this video is from scikit-learn make circles. So this is the data that we'll be utilizing. So make circles is a popular data set provided by scikit-learn to work with binary classification problems, and using this format we can use make circles dataset. So without talking further, let's go to Google Colab. This is my Google notebook, and let's connect to the runtime and let us import our dataset. So in this video, we'll be building multiple models. First, we'll be building baseline model, and then gradually we'll be improving our baseline model, and finally we'll have a model that is capable of separating class. So don't worry if you don't understand something in the beginning, but I promise at the end of the video, you will understand everything. So first of all, we need to import this dataset. So to import the dataset, first of all, let's import scikit-learn, import scikit-learn, and also from scikit-learn.datasets, import make circles. Let us run the cell. Okay. So now let's import the data. So how many samples do we want? Let's say we want 1000 seems a good number, and X and Y. So X is going to be our features, and then Y is going to be our label. So X can be some tensor, and then Y will be whether it belongs to some class A or class B. Don't worry, you will understand it once we import the data and visualize it. For now, let us just import the data. Click circles, and we have to pass number of samples. Number of samples, we need to pass noise. So we're adding noise to the data so that data is not properly structured. So noise of 0.03 seems a good number, and random state. For reproducibility, we will pass random state of 42. So let's run this state and let's check the length of X and Y. Length of X and then length of Y. So okay, the length of X is 1000 and the length of Y is 1000 because we have imported 1000 data set from make circles. So let's visualize the data. Let's first print first 5 samples of X and first 5 samples of Y. Print format first 5 samples of X, and then we want first 5 samples. Similarly, let's print first 5 samples of Y. Format first 5 samples of Y, first 5 samples of Y. Now let's run the cell and let's visualize the data. Okay, so we can visualize the sample of X. We see that this is a two-dimensional vector, and it has features like 0.75, and this we can assume this is x1 and this has x2, and then y is something like 1 or 0. This is one dimensional and it's either 1 or 0. So for example, if our data is something like this, then the label will be 1, and if data is something like this, then label will be 0. So let's further visualize this using a data frame. So to build a data frame, let's import pandas. Import pandas as pd circles equals to pd dot data frame. So we're going to visualize the x and y data using data frame. So we have two features, x1 and x2, and we'll also print another column to see the label. So in the form of dictionary, first column is x1, and we want to print all the row but from the first column. Similarly, we want another column x2, and we want to print all the row but from first column, I mean the second column, first index. And third column we want to name is as label, and we want all the values of y. So let us visualize the first 10 samples from the data frame. CIRCLES circles. Okay, so this is x1, this is x2, and the label is 1. Similarly, this is x1, x2, and the label is 0. So again, let us further visualize our data using matplotlib. So we want to plot our all the data points of 1 and all the data points of 0. So let's plot visualization using matplotlib. So let us import matplotlib. Import matplotlib.pyplot as plt. So we want to plot a scatter plot, scatter, and x as we want all the row from x but first column. Similarly for y, we want all the row from x but the second column, and c as y, which is the label, and let's give a good color. cmap equals to plt dot color map dot red, yellow, and blue. Let us run and visualize our labels. So you see our labels are in circular format. So there are red labels which we can refer to as 1, and there are blue label which we can refer to as 0. So the final model that we want to build is that a model is capable of separating red dots from blue dots. So we want to build a model that is capable of separating red dots from blue dots. So how to separate red dots from blue dots? Can we separate using a line, or we need multiple lines, or we need some non-linear lines to separate red dots from blue dots? That is something we will test and experiment further. So now we have data, but before feeding our data to the model, we need to change the data. Currently our data is in numpy, which is nd array, and we have to pass the data to the model, which means we have to first convert nd array to tensor. So first let us import torch, and let us change x to tensor and type float. So torch dot from numpy, currently it is on numpy, so we want to convert from numpy to tensor, and then convert into the type of torch dot float. Similarly, we want to convert y from numpy to tensor, and then type as torch dot float. Torch dot float. So let's run the cell. Okay, the cell has run, and now let's check first 5 samples of x and first 5 samples of y, and let's check if it has been converted to tensor and the type is float or not. Print f first 5 samples of x. I highly recommend you to write print statements and visualize, because this makes it easy. First 5 samples of x, and similarly let us print first 5 samples of y. Samples of y. On to the next line, and y first 5 samples. Okay, we can see that our x and y data has been turned into tensor and it has been converted into floating point. Okay, so now let us check the shape. The shape of x should be two-dimensional and the shape of y should be one. So let us just run a cell to visualize the shape also. Y dot shape. Okay, we can see the shape of x is two-dimensional. We have 1000 data points, and this is one-dimensional and it has 1000 data points. So x has features x1 and x2, and similarly y is the label, which is either 0 or 1. So before feeding data to our model, we need to split our model to train and test dataset, because using train dataset we'll be using to train our model and we'll be using test dataset to evaluate our model. So first of all, let us split our dataset to two parts, training and testing. So let's perform train test split. So to perform train test split, we need to import model selection from sklearn. From scikit-learn.model selection, import train test split, and we need to pass our feature, our label, and then test size. So generally we put test size as 20% and train size as 80%. That is the standard. But sometimes you often see there is train size as 70 and 10 as validation and then 30 as or 20 as test. But this time we're only going to create train and test dataset. So let's keep our train datasets as 80% and test dataset for 20% of the total. So test size will be 0.2, which is 20%. And let's add random state for reproducibility 42. And what will our train test split return? Our train test split will return, we can view the doc string. Yes, train test split will return x train, x test, y train, and y test. So let us create a variable for each of those: x train, x test, y train, and y test. So let us run the cell. Okay, so what should be the length of our x train, x test, y train, and y test? Let us print it out. X test, length of y train, length of y test. So I guess the length of x train should be, because there are 1000 data and 80% is for training, means x train and y train should be 800 and x test and y test should be 200. So yes, x training is 800 and then testing is for 200 data sets. So now let's follow a good practice. Let's create a device agnostic code, because every time you run your code doesn't mean you will be on the same runtime. For example, right now my Google Colab is running on CPU, but next time when I run, maybe it will run on GPU, and on that time my device should be CUDA. So if your model is on one device and if your data is on another device, then you will face error. So to mitigate that error, we need to make device agnostic code. Don't worry if you didn't understand, you will know more about this as we move further. But for now, just keep in mind that your model and your data should be on the same device. So for that, I'm going to create a device agnostic code. So from torch, import nn, and I need to make device agnostic code here. Okay, device equals to CUDA if torch.CUDA is available. So if torch.CUDA is available, if this expression is true, then set my device as CUDA, otherwise set my device to CPU. So let us view the device. Again, since my Google notebook is running on CPU, this time my device should be CPU. Here it is, my device is currently on CPU. So now let us print. Okay, now let us create first model. So how we are going to build our first model? So we will be instantiating nn.module class. Okay, let us first understand what is nn.module class. You see, nn.module is a base class for all neural networks. So yes, this is exactly the way we are going to create our model. So we will be creating a child class of nn.module class, and then we will be creating our model in this way. So let us create our model class, and let us name this as circle model version 1, because we are going to be building multiple versions, because we are going to be experimenting with our model and see which model gives the best result. So we need to make a child class of mn.module. Let us create a constructor, self parameter, and let us call the base class constructor. It should be underscore underscore init. Now, okay, in this neural network, in our first model, we will create two layers. One will be input layer and another will be output layer. We'll not create any hidden layer. And our input layer should accept two data, which is x1 and x2, right? And our output layer should give whether it is whether it belongs to class A or class B. So our output should be 1 and our input shape for the input layer should be 2. So let's create first layer, self dot layer 1 nn dot linear. So we'll be creating linear layer, and the formula for linear layer is y equals mx plus c, y equals mx plus c, where m is the slope, x is the data, and c is the bias. Or in neural network, m is weight, x is our data that we want to pass to our model, and c is the bias. So behind the scenes, our linear layer will apply this mathematical function. So nn.linear. So what should be the input shape? The input shape should be 2, because in our the data that we are going to pass to our model has x1 and x2. There are two features, so we'll keep in features as 2. And hidden units, how many hidden units we want? So hidden units are these nodes. So how many hidden units do we want? Let's say we want 5 hidden units. So this can be absolutely random, this can be absolutely your choice, and this is something that we want to optimize further. But for now, let us randomly keep a number. This time I have selected 5. So let me create another layer for output, nn.linear, another linear layer. So what should be the in features of this layer? The in features of this layer should be exactly the out feature of the previous layer. So since the out feature of this layer is 5, so the output from this layer is going in this layer. That's why the in feature should also be same as this, which is 5. And since this is the output layer, what should be the out features? 1, because we want if it belongs to class A or class B. So we've created 2 layers. Now let us create forward method, because that is what is needed. We need to create a forward method def forward self, and x is going to be the data that we are going to be passing to our model. Return, so we will be passing our data x to the first layer, and the output of the first layer should go to layer 2, and then layer 2 will be the output. So self dot layer 1 will be passing our data to the layer 1, and the output of layer 1 should go to layer 2. Okay, we run the cell. Okay, this is our first model. So let us now instantiate the model. Oops. Okay, instantiating the model. Instantiating the model. So let us name the model as model 0 because we will be creating for the models and they will be model 1, model 2 and so on. So our first model is model 0. So we'll be instantiating circle model 1, and again, as I told you that we need to send our model to the same device and the data also should be in the same device. So let us send our model to the target device, which is CPU. Okay, model 0 is our first model of the video. So let us visualize model 0. We have layer 1, we have layer 2. Layer 1 takes two features, x1 and x2, and layer 2 is the output layer which tells if it belongs to class A or class B, if it is red dot or blue dot. So since our model is on target device, the parameter of our model also should be in the target device. But how does our model parameter look like? Let us visualize state model 0 dot state date. Okay, these are the parameters of our model. So basically in the beginning, while we instantiate the model, our model parameters are absolutely random. And this is the reason why most of the times our initial model before training will give very poor results because these weights and biases are not optimized. And further, when we train our model, our weights and bias will be optimized and our model will be able to give accurate results. So right now our model is on target device. So we need to send the parameters of our model also to the target device. So let's send our model parameters to the target device. Model 0 dot parameters dot device. Okay, we've sent our model parameters to the target device. We've sent our model to the target device. Now what we want to do is we want to set up loss function and optimizer. So loss function is used to calculate the loss and optimizer is used to optimize your model parameters. So let us set up our loss function. Set up loss function, loss fn equals to nn dot bce with logits loss. BCE with logits loss. So this is the loss functions that we'll be using. Now what is BCE with logits loss? So BCE with logits loss is a loss function that combines a sigmoid layer and BCE loss in one single class. So what is happening is this function will accept a logit. A logit is a random prediction that is made by your model, and it internally applies sigmoid layer and then it will calculate the loss. So you will understand further down the video, further the video progress, you will understand more about how BCE with logits loss work. But for now, just understand that this is the loss function that we'll be using, and it internally applies sigmoid layer and will calculate the loss. So let's write comment. Internal application of sigmoid layer, which is the activation function, and calculates the loss. So let us set our optimizer. So optimizer is used to optimize our weights and biases. At the beginning, the weight and biases are completely random. So while training our model, we want to optimize. So we're selecting our optimization algorithm right here. So torch.optim.sgd, and the optimization algorithm that we have selected is stochastic gradient descent. Params equals to, we need to pass the parameter of our model, model 0 dot parameters, and then the learning rate. So learning rate is how fast to change the parameters of a model. For now, let us select 0.01. Let's run the cell. So remember, loss function calculates how bad your model was, how bad your model predicted, or how far the model prediction and the true label is. And optimizer is used to improve your model. So what will optimizer do is that it will optimize the weights and biases and make the model more accurate. So let us see how the model, let us understand how BC with logits loss actually works. So we have confusion in this, right? So let us see how this works. So for now, let us okay, at the beginning, the weights and biases are completely random. And I said when the weights and biases are completely random, not optimized, then your model will predict very bad results. So let's see how bad it will predict. So we will set our model 0 to evaluation mode. When you set your model 0 to evaluation mode, it will stop gradient tracking and so on. With torch.inference mode, this will make our training faster. So what we want to do is we in our model we want to pass X test. So X test is our data that we have separated for testing. We want to send X test to model 0. So model 0 will output raw logits. So let's name it as Y logits. So what we are doing is we are passing data to our neural network, and our output layer is out our output layer gives raw logits that is stored in Y logits variable. But before passing our data to model 0, we have to put our data to the target device because model 0 is currently on CPU, model parameters is on CPU, and we also need to send our data to the CPU. So let us put our data to the CPU to device. Let's run the cell. Okay, so let's visualize how Y logits look like. Y logits. Let us view first 5. Okay, this is how Y logits look like. These are complete random values generated by our model because the parameters have not been optimized. Our model output layer will give Y logits. These are raw numbers. Now what we want to do is, I told that our loss function will convert our logits to a numerical stable number using sigmoid layer. So let us see how it will do that. So instead of using loss function right now, let us see how this actually works. Let us write our manual code for now. So our model has given Y logits. So let us apply sigmoid function manually and see how the output will look like. Torch.sigmoid Y logits, and let us store in the variable Y pred. And let us again visualize first 5 data, first 5 predictions, Y preds. Okay, so you see how our Y logits has been converted to this format after applying sigmoid layer, sigmoid activation. So sigmoid is responsible for converting our raw logits to a numerical stable way, numerical stable format. So if you search sigmoid activation function, this is what is happening behind the scenes. This is the mathematical function that is being applied, and it will, okay, the sigmoid activation function has applications to machine learning through its operation in neural network. As a matrix, okay, the whole network is formed by chaining such matrix multiplication together. So what our sigmoid function is doing is it is converting our raw logits to a numerically stable format. So the logits has been converted to numerically stable format, but this is not the label. Our Y label, so if you look, our Y test is something like this, and we want our model prediction to be like this, right? In the format of either 0 or 1. We don't understand this. So how to convert this to zeros and ones? To do that, we will round this. So our model has given raw logits. We have applied sigmoid activation, and to convert these to ones and zeros, we will apply round. So torch dot round y preds. So when we round y preds, it will provide output like 0 and 1. Let's store that in the label y labels, in the variable y labels, and let us visualize that again. Labels first 5. You see, now our model prediction is correct. This is the format that we want. Our model will give raw logits. We will change that. We'll pass to sigmoid activation and turn that into numerical stable format, and then we'll convert to ones and zeros by rounding them. So let's see how well our model predicted. Let us also print first 5 sample of y-test. You see, this is the model prediction and this is the actual ground truth. So model has predicted all ones, but the actual output should have been 10101. So again, the model is predicting so bad because currently the weight and bias is completely random, and the whole essence of training our model is to optimize the weights and biases in such a way that the model will give accurate predictions. So what we want to do now, since our model has performed very bad, so now what we want to do is we want to train our model. We want to optimize these weights and bias so that our model will be close to the ground truth. So let's build a training and testing loop. Building training and evaluation loop. So let me set torch dot manual seed as 42 for reproducibility. This is for reproducibility. And for how many epochs do we want to train our model? Let's say we want to train our model for 100 epochs. Again, we are building our baseline model. We are training our baseline model. So as I told you, our model 0 is on target device. We also need to put our data x train, y train, x test, and y test to the target device. So let us put the data to the target device. So x train and y train should be in the target device. X train to target device, which is CPU for now. Y train dot to target device, and similarly we want to convert our y test, sorry, x test and y test, right? X test and y test to the target device. X test dot to target device, and then y test to target device as well. Okay, so now let us loop through each epoch. Let us create a loop for epoch in range epochs. So now let us train our model. Before training our model, let us put our model to training mode. So with this line, we are putting our model 0 to training mode. Put the model to train mode. And now what we want to do is we want to pass our x train to the model 0. And the model 0 will output raw format, raw logits, and then we will convert the raw logits to something like zeros and ones by passing to sigmoid layer, and then so on. Let's follow the steps. So we will pass x train to the model, and by passing x train to the model will output y logits. These are numerically unstable. So to convert to numerically stable way, we need to pass our logits through sigmoid activation and then round it, and then we'll get in the format of zeros and ones. But what I'm thinking is, before doing this, we want to calculate the accuracy of our training and testing, right? So let us create another cell just before this and calculate the accuracy. So let us create a function, def accuracy function, which will accept two labels, and then the prediction of our model. So what will this model do? This function will return the accuracy percentage. So we want to calculate the accuracy of our training and testing. So for example, if our model has predicted something like 11100 and the actual label was 10110, then the accuracy should be, okay, this first has been matched, this second doesn't match, this match, and this match. So out of 5, 1, 2, and 3 match. So 3 divided by 5 times 100 will give the accuracy, right? So this is exactly what we want to do. We are accepting true labels and then the prediction of the model, and now we'll calculate the accuracy. So torch dot equal, let's see how many of them are equal. We want to compare y true and y pred, and then we want to calculate the sum item. So this will give how many of the predictions were correct. So let us store in the variable correct, and now we'll divide this correct by the length of y pred, and then we'll multiply with 100, which will give the accuracy percentage. So this is giving me the accuracy percentage, and I will store this in variable accuracy, and let me return this variable accuracy. So this function will now give me the accuracy percentage. So right now let's be back to our training mode. We have set our model to training mode. We have passed xtrain to the model. Our model has output some y losits. Now we want to convert our y losits to something in the format 1 and 0. So what we will do is we'll pass y losits to sigmoid function y losits, and then we'll round the output of the sigmoid. So this will give me the format exactly like this, 1 and 0, and let us store this in the variable y pred. Let us calculate the accuracy by using the accuracy function that we just defined. Accuracy function y true. First parameter is y true. So what is y true here? We're passing xtrain, so the true value of this is y train. So y train, and then y pred is the model prediction, which is y pred. Also we want to calculate loss, so we'll be using the loss function that we created. The loss function is BCE with losits loss. So this loss function expects losits. In our case it is y losits. Again, losits are numerically unstable, and this is what our loss function is expecting. So we are passing y losits, and what is the true? Y train. So here we are calculating accuracy. Here we are calculating loss function, the loss, how far our model prediction and the actual prediction is. So now what we want to do is optimizer 0 grad. Why are we doing this step? Because every time our optimizer will append further, like the gradients will be appended in a list. So we want to reset the list every time we do back propagation, right? So this step is for resetting the parameter for next backward pass. Again, if you do not understand now, just bear with it, you will understand further. Loss backward, so this is for backward propagation, backward pass, and optimizer step. So here we are performing backward propagation, and in optimizer step we are optimizing the model parameter. Optimize the model parameter. So let us understand what is happening in this training loop. So first of all, what we are doing is we are setting our model to training mode. we are passing X train through our model, and then the model will output raw losits, which are numerically unstable. So what we are doing is we are passing these losits to our loss function, and the loss function is BC with losits loss. The loss function will calculate the loss, how bad our model predicted, and then we what we are doing is we are doing backward propagation. So before we are going from input layer to output layer. Now in back propagation, what we are doing is we are going from output layer to input layer. And when going through each layer backward, we are optimizing the weights and bias of each node. That is what we are doing here. Setting our model to training mode, passing X train to our model, which will give losits. Losits are numerically unstable. So what we are doing is we are passing losits through sigmoid and then doing round. So while we round our losits, it will look something like 1 and 0. And we are passing this ypred to accuracy function because y true is 1 and 0. And for that reason, ypred also should be in 1 and 0, right? So we are passing this to our accuracy function. This will return the accuracy percent. Loss function will tell us how bad our model predicted. And here we're resetting the parameter for next backward pass. We're moving from output layer to input layer by optimizing the model parameter. And in this step, we're actually setting the model parameter. We're updating the model parameter. So this was our training loop. Training loop is done. Now we want to create evaluation loop. So now we will set our model to evaluation mode, just like we did before. This will turn off gradient tracking and so on. With torch.inference mode, what we are doing here is we are turning off the gradient tracking, and this is making the training loop faster. So here we passed, while training we passed ytrain, while testing we'll pass xtest to our model, xtest, and again the model will output raw losits. We will store this in the variable test losits, and again we'll convert losits to something which is numerically stable. For that we'll pass our losits to through sigmoid layer, and then we'll round it. So let us pass our losits through sigmoid, test losits, and then again we'll pass to torch dot random. So now our this is in the format of ones and zeros. So let us store this in the variable test pred. Now let us calculate the test loss. Calculate the test loss. So let us call loss function. We want to send our losits because that is what our loss function accepts, because we are using BCE with losits loss. So we want to pass test losits, and the actual, which is y test. For x test, the actual label is y test. So this is the loss. Let us store in the variable test loss. So likewise we did in the training, we also want to calculate test accuracy. So we want to call our function that we made. This is the custom function which accepts y true. Y true is y test, and y pred is test pred. So this is actually in the format of zeros and ones. So now what we want to do is let us visualize how each epoch, how our model is performing in each epoch. For that we'll write some print statements for visualization. So we are going through 100 epochs. So let us, if epoch is divisible by 10, then we want to print. So for each 10 epochs we will display print statements. So we will display epoch, which epoch it is currently running. We will see the train loss, the train accuracy, Again, let us view 5 decimal places of loss. And for train accuracy, so train accuracy is in this variable accuracy, and we want up to 2 decimal places. Now similarly for test, we want to see test loss variable, and we want 5 decimal places. Test accuracy, we want up to 2 decimal places. So let's run this cell. Okay, we have an error. Okay, seems like our y train is in this format, and our loss function expects our y label to be in this format. So we want to add extra dimension. So to add extra dimension, what we want to do is, let's squeeze squeeze, and then similarly here also squeeze. Let us run the cell. Module object is not callable. Okay, what error is this? Okay guys, there was a mistake here. So we wanted to round. In training we did round, but here we did random, so it should be round actually. So let us run. Okay, so we can see each epoch the training and test accuracy for train and test. So in 0 epoch we can see that train loss is 71%, and as the epoch pass, our model does not seem to be learning quite well, and the accuracy for train also does not seem to be improving, and the same is the case for test. The accuracy is not improving, the loss is not decreasing. So what our ideal model should have been is, the accuracy should have been increased and loss should be decreasing. So clearly model 0 is not performing well. So why model 0 is not performing well? Again, it might be because of various reasons. It might be that the hidden units we want, if we add more hidden units, the model will be performing well. And if we add more hidden layers, maybe it will get more chance to learn the patterns and it will perform well. Let's test it out. Let's talk less and just build our next model, and let's see how it will perform. But currently our model clearly does not seem to be performing well, because accuracy is not going up and the loss is not going down. So again, let us visualize how it looks. Let us visualize how it separates red dots with blue dots. We want our ideal model to separate red dots with blue dots. So let's see how model 0 is currently separating red dots with blue dots. So let us visualize. And for that, again, there is a helper function that we want to use. I'll provide you the link in the description. So this is the URL that you want to go, and there is a function called plot decision boundary. We want to import this function in our notebook. So let's import this whole file and then import this particular function. So we want to make a GET request to that particular URL. So from path lib import path, import requests from path lib import path. If path, we want to check if helper functions.py is already downloaded, then we simply just want to import it. And if helper functions.py is not downloaded, then we want to download it. So that is what we are doing right now. Helper functions.py. If this already exists, then what we want to do is we want to skip the download. So let's print something like helper functions.py already exists, skipping download. So if helper functions.py is already available, then we want to skip the download. If it is not available, then we want to download. So to download, what we want to do is we want to make get request to this URL, and then we will create a file and then write the contents of this URL. So let's make a get request. So request dot get request for in this URL, and then what we want to do is we want to create a new file called helper functions.py, write byte as file, and in that helper functions.py file we want to write all the contents. So request.content. Okay, response object has no content. Request dot, okay, typo here, content. Okay, helper functions.py already exists, so skipping download. So looks like in my Google Colab helper functions was already there. So if helper functions was not there, then it would have made a request to get request to this URL, and it would have created a file, and then it would have write all the contents in helper functions file. So let me delete this, and let me run this cell again. So okay, now let me come here. Okay, helper functions.py has been created, and let me check. Okay, all the code has been written in this file. So what we want is from this helper functions.py, from helper functions, I want to import plot decision boundary. Okay, so currently what I want to do is by using this function, I want to visualize how my model 0 was separating red dots with blue dots. So plt dot figure, so figure size 12.6. Let me create a subplot of 1, and then I want 2 figure at 1 row, and then for 1 plt dot title. So first we want to visualize how our model was separating red dots from blue dots in training, and also we want to do the same for test. So let's do for train plot decision boundary. Let us call the function, and this function we want to pass our model. Also we want to pass the data x train and y train, and similarly we want to create another subplot plt dot subplot, give me suggestions, subplot 1 to 2 plt dot title, this is for test, plot decision boundary, we want to pass our model 0, and in this case it's for test, which is x test and then y test. So let us run the cell. Okay, you can see our model was not separating red dots from blue dots, and that is why it was performing so poor. Our model was not learning. You can see the accuracy was 50%. So out of 100 samples, it was only getting 50 samples correct, which is, it was clearly doing as good as guessing. So you can see in training, it was not able to separate red dots with blue dots. And again, in the test also, it was not able to separate red dots with blue dots. So clearly model 0 was not learning anything, and that is why it performed very, very bad. So what might be the reason the model was not performing good? Maybe if we increase the hidden layer, maybe if we increase the number of hidden layer, it will do well. We don't know, we will experiment. And maybe if we add more hidden units in a hidden layer, it will do good. Maybe, we don't know. That is what we want to do in machine learning. We want to experiment. Here we created our base model, model 0. Where is our model? Okay, we created our base model, which is model 0. Clearly model was not doing correct, so we want to upgrade our model and make another version of the model, and let's add more hidden layers and hidden units to the new model and see if it can learn, if it can separate red dots with blue dots. So let's make another version of the model. So from base model, we're creating another model. So similar process, we're going to do all the things similar that we have just done before, but we want to create subsequent models and see which model performs well. So circle model v2 this time, and then dot module. And as we subsequently build model, you will understand how everything is working. So maybe in the first try, you did not understand how everything was working, but as we build models further on the video, you will understand how everything is working exactly. I promise, just wait until the end of the video and you'll understand everything. So we want to create a constructor and pass self. We want to call the superclass constructor. Now what we want to do is, before we had just one hidden layer, now we want two hidden layers. So first we want to create a layer 1 and then dot linear, first linear layer. What will be the in feature? In feature is 2 because we have x1 and x2, we have two features. And then out features will be how many hidden units we want. Before we created, how many hidden units we had? Okay, before we had 5 hidden units. So this time let us create 10 hidden units and check if our model performs well or not. Self dot layer 2 and then dot linear in features. Now what should be the in features? It should be 10 because the output from layer 1 is being accepted by layer 2. So since the output is 10, it should accept 10. So we want 10 hidden units, and then out features should be 10 because this time we are creating 10 hidden units and one additional hidden layer. Self dot layer 3, and this is going to be our output. In features, this should be 10 because it should match, and out feature should be 1 because we want if it belongs to class A or class B. So our model should output something like class A or class B, red dot or blue dot, 1 or 0. So it should output 1, right? So this time what we have done is we have created an additional layer. We have increased our hidden units, and now we want to check if it does well. But we need to create a forward method. Self x, we want our data to be passed through layer 1, and the output of layer 1 should be passed to layer 2, and the output of layer 2 should be passed through layer 3. So let us pass our data through layer 1. The output of layer 1 should go to layer 2, and again the output of layer 2 should go to layer 3. Okay, so let's run. Okay, so now let's instantiate the model. Before we had model 0, now we want model 1. Circle model v2, and again, good practice, we want to send our model to the target device. Let us print the model. Okay, our model has layer 1, one additional layer, hidden layer this time, and finally the output layer that will give whether it is 1 or 0. So we have sent our model to the target device. What next should we do? We need to send our model parameter to the target device. So next, model 1 dot parameters dot device. So our model 1 parameters have been moved to the target device. Our model 1 is in the target device. Model parameter is in the target device. Now what we want to do is let's visualize model 1 state bit. We want to visualize, let us visualize models initial weights and bias. So these are the weights and bias, and you can see the number of weights and biases has been increased because we have added extra hidden layer and more hidden units. So again, This is completely random. So we want to train our model and optimize this. So let us create loss function and optimizer. Loss function and optimizer. So loss function is going to be similar like before, and optimizer is going to be similar like before. And then dot BCE, which loss, and optimizer is going to be torch dot optim dot stochastic gradient descent, where the parameters will be model. This time it's model 1 dot parameters and learning rate. Okay, before the learning rate was 0.01. This time I'm setting learning rate to 0.1, just experimenting and seeing whether model will be good or bad. So okay, we've set our loss function and optimizer, we've created our model, we've sent our model to the target device, we've sent model parameter to the target device. Now what is the next thing? Training and evaluation loop. The torch.manual seed to 42 for reproducibility. So before we created 100 epochs, let us create 1000 epochs this time. Let's see how our model performs. So with more epochs, we're giving more chance to our model for learning the patterns in our data. So our model is on target device, model parameter is in our target device. Now we need the data that is going to be passed through the model. The data should also be in the target device. So xtrain, ytrain, xtrain dot to target device, ytrain should be in the target device to target device. Similarly, we want to pass xtest and ytest to the target device. Xtest dot to target device and ytest dot to target device. So xtrain is to target device, and then xtest, ytest is in the target device. Okay. So now what we want to do is we want to create training and testing loop. So let us create a loop for each epoch in range epochs. This is the similar that we did before. So let's create our train loop. So we want to set our model to training mode. Then we want to do forward propagation, which is we want to pass our xtrain to the model. Also, we know that we have to add an extra dimension, and this dot squeeze will add extra dimension. And what will this return? This will return raw numeric output, which is losits. This is numerically unstable. So what we want to do? Yes, we want to pass it through sigmoid activation, and then we'll round it. So torch dot sigmoid y losits. Then after passing through sigmoid activation, we want to round it. So now this will be in the format of zeros and ones. We want to store in the variable ypred. Now let us calculate accuracy. We have created our custom accuracy function, which accepts ytrue. Ytrue is ytrain, and then what is ypred? Ypred is the ypred, yes. So this is the format of zeros and ones. This is also in the format of zeros and ones. So our accuracy function will return accuracy percentage. We want to calculate loss. We have loss function BC with losits loss, which will accept raw losits, and raw losits this time is y losits, and the actual label is ytrain. We want optimizers on zero grad because gradients will accumulate over time, and we want to clear that before backward propagation. Optimizer. Now we want backward propagation, loss step backward. Here we are going from input layer to output layer, and here we are going from output layer to input layer. So optimizer dot step. Here we are actually changing the weights and biases. So this is the important step, right? So here we are updating the model weights and biases. So this was our training loop. Similarly, we want our evaluation loop. So we want to set our model to evaluation mode. And then what we want to do is, by setting our model 1 to evaluation mode, we are turning off gradient tracking and so on, which starts dot inference mode. So this will make our training loop faster. We will pass xtest to model 1, and also we will apply squeeze method, which will add an extra dimension. Model 1 will output logits, which will store in test logits, and then we will convert our logits to the format of 0 and 1 by first passing our logits through sigmoid activation, and then again we will round the values. Okay, now it's in the format of zeros and ones, and we will store that in variable test spread. Now we want to calculate test accuracy. So to calculate test accuracy, what we want to do is call our accuracy function. So we want to store that in test accuracy variable, call our accuracy function, which will accept true value, which is, in our case, it's for x test, our true value is y test, and y pred is this time test pred. So this will return accuracy percentage. Now we want to calculate test loss as well. Call our loss function, which will take test losits, and then the actual value is y test. So now let us add print statements. So this time we have 1000 epochs. So let us, for every 50 epoch, let us add a print statement so that we can clearly see how each training and testing loop is going on. So if epoch divided by 50 and the remainder is 0, which means that epoch is exactly divisible by 50, then we want to print what we want to print: epoch, which epoch it's currently on, and then what do we want? We want train loss. Train loss is in the variable loss, and then we want first 5. We want train accuracy, it's in the variable accuracy. We want first 2 decimal places, and similarly for test, we want test loss, which is first 5 decimal places, and test accuracy in the variable test accuracy, first 2 decimal places. So let us run this cell and let's see how our model is performing. Oh no, train loss is not going down. Train accuracy is not going up. It's going up, but very negligible. Test loss is not going down, and train accuracy, test accuracy is not going up. In fact, it is decreasing. So clearly our model 1 is also not performing good. So in our model 0, we found out that it was not going good because it was not able to separate red dots from blue dots. In model 2, we added extra hidden units and a hidden layer, and again it is not able to perform well. Again, let us do similar. Let us copy this, let us paste here. This time it's model 1. Let us visualize how it's separating our blue dots and red dots. Okay, similar, it's not able to separate our red dots with blue dots. In the train also, in the train and in the test also, it is not able to separate our red dots with blue dots. So clearly model 1 is also not doing good. So can you put a guess, a random guess, why it's not doing well? Because we're trying to separate red dots from blue dots using straight line, and it's almost impossible to separate red dots with blue dots using straight line. I mean, it has to be straight line, and the straight line, straight line, straight line, straight line, straight line. It's extremely difficult, and it's almost impossible. So what do you think? What should we do? So we want to create another model. Let us create another model that can learn nonlinear patterns, and then let us see if it can actually, separate red dots with blue dots. I think we should try that. And and the activation function we need for another model is ReLU. So ReLU stands for rectified linear unit. It's a activation function which is used in deep learning models such as ours. And what this activation does is it returns for positive value, it returns the positive value, and for negative value, it returns 0, which means that through ReLU activation function, only positive values can pass forward. So ReLU activation function is responsible for no, it's a non-linear activation function. So it helps our model to learn non-linear patterns. Clearly, we cannot separate red dots with blue dots using just a straight line. We need to introduce a activation function like ReLU, which is a non-linear activation function, which helps our model to learn non-linear pattern. So let us create another model. So our base model was model 0. We added more hidden layer and hidden units on model 1, and clearly it was also not doing well. So let us create another model. Class circle v3. Now again, this is going to be the same approach, iterative approach. This is what we do in machine learning. Module, and then the constructor, super, call the superclass constructor. And then this time what we want to do is we don't want to add extra hidden layers. In fact, we want a nonlinear activation function called ReLU. So let us create our first layer, layer 1, nn dot linear, first linear layer, which in features should be 2 because we have two features x1 and x2. Out features we can set 10 hidden units. Self dot layer 2, another linear layer which in features should match the out features of the previous layer, so it should be 10, and out features we can set as 10. So this is the hidden layer. Layer 3, self dot layer 3, another layer, and then dot linear, in features match this, and out features we can set as 1 because this is the output layer, and output layer gives, actually it is class A or class B. And the extra thing that we're doing here is adding another activation layer called ReLU layer, and this is non-linear activation function. So this layer is responsible for making our model learn non-linear patterns. So let us create our forward method, self x, and what we want to do now, we want to pass our data through layer 1 to layer 2, and then we want to pass through layer 3, or we want to pass our data to layer 1, then pass to ReLU so that the model has chance to learn non-linear patterns, and then again pass through layer 2, then again pass through ReLU, and then pass through layer 3, and finally it will output some class, whether it is class A or class B. So what we want to do, first of all we want to pass our data through layer 1, and from layer 1 we want to pass it through ReLU activation so that the model has chance to learn non-linear patterns. After passing through ReLU, again we want to pass through layer 2. After passing through layer 2, again we want to pass through ReLU, and after passing through ReLU, finally we want to pass through layer 3 because layer 3 gives the output. So first passing our data through layer 1, then ReLU, then layer 2, then ReLU, then finally our output layer 3. So you can see first we pass through layer 1 and then it will learn nonlinear patterns, again through layer 2, then again learn nonlinear patterns, and then again through layer 3. So it's a combination of straight line and non-straight lines. So to separate these red and blue dots, maybe we need straight lines also and non-straight lines also. That is what we are trying to do by building this model. So let's instantiate the model and name this as model 3 circle model v3. Again, standard practice, we want to, pass our model to the target device, and also we want to pass the parameters of our model 3 to the target device. Model 3 dot model 3 dot parameters dot device. Let us visualize the parameters of our model 3. Model 3 dot state predict. So again, these are completely random at the beginning. We want to optimize this so that our model will predict accurately. So now what we want to do, we want to create loss function and optimizer. So loss function equals nn dot bc with logits loss, same as before, and optimizer torch dot optim dot stochastic gradient descent, and our optimizer will accept model parameter. This time it's model 3 dot parameters, and the learning rate will be 0.1. This is absolutely up to you, and for now we are setting as 0.1. Let us run this cell. We have set our loss function and optimizer. Now again, the same thing, we want to build training and evaluation loop. So let us quickly build training and evaluation loop. This time we want to train for 1000 epochs, and let us again good practice, device agnostic code. We have our model in the target device, we have our model parameter to the target device. Now we want to pass our data that goes through the model also to the target device. So xtrain, ytrain, xtrain to the target device, and then ytrain also goes to the target device. Similarly, our xtest and ytest also should go to the target device. Xtest to target device and ytest also to the target device. So now let us create the loop for epoch in range epochs. So let us create our train loop. So what we have to do, I think, as we have built so many models, I think it is now clear to you that we have to first set our model to the training mode. Then we will pass our xtrain to the model. So model 3, we want to pass xtrain and we want to squeeze it because we want to add an extra dimension, and our model will output logits, which we want to store it in ylogits variable. Now we want to convert logits to the format of zeros and ones, and for that we need to pass our logits to sigmoid layer, and then we want to round it. So torch dot round torch dot sigmoid y logits, this is in the format of zeros and ones, and then let us store in the variable ypred. Let us calculate accuracy. We have our custom built accuracy function ytrue. Ytrue is ytrain, and then ypredicted is ypred. Okay, we have calculated accuracy. Now let us calculate the loss too. Our loss function accepts logits, y logits, and then the true value, which is ytrain, and then optimizer dot zero grad, because our gradients accumulate over time, and in the next backward pass we want to clear out the accumulated gradients. So after we create, we want to perform backward propagation. Then we want to optimize our model parameter. So this was training loop. Similarly, we want to test loop. So we want to set our model 3 to evaluation mode, and this will turn off gradient tracking. Now again, we to make our evaluation loop faster, we want torch dot inference mode, and we want to pass x test to the model. Model 3 x test squeeze for adding extra dimension. Model 3 will give us logits which we want to store in test logits variable, and then we want to convert it into ones and zeros. So what we want to do is we want to pass through torch dot sigmoid. Now the value are numerically stable. Now we want to round it so that it is in the format of zeros and ones, and now we want to store in the variable test spread. So now let us calculate accuracy. Test accuracy equals accuracy function true value. What is the true value? True value for x test is y test, and predicted value is test pred. Now let's calculate test loss as well. We have done this multiple times. So y loss function accepts losits, and then the true value is y test. Now since it's 1000 epochs, so let us print for every 100 epoch. So if epoch is exactly divisible by 100, then we want to print. If for epoch divided by 100 gives the remainder 0, then we want to print. For visualization, what epoch is it? Epoch train loss we want 5 up to 5 decimal places. Train spelling is wrong here. Train accuracy. So what's the accuracy? Accuracy, and we want up to 2 decimal places. Similarly for loss, for test, we want test loss to 5 decimal places, and test accuracy 2 decimal places. Now let us run this cell and let us visualize how our model is learning. So okay, now our model seems to be learning quite well. The accuracy, train accuracy is increasing. Our loss is decreasing, but not very good. But train accuracy is decreasing. Train accuracy is increasing. So it is 74% accurate, which means out of 100 samples, it predicts 74 correctly. And for while testing, out of 100, it predicts 79 accurately. And the test loss is also going down. So looks like our model is going in the right direction. It's learning. It's learning well, right? So let's see how it is. Let's visualize it again. Let's copy this code. Let's visualize how it is actually separating red dots from blue dots. Now this time we have added ReLU activation, so it should be able to learn non-linear patterns. So let us see. Okay, our model seems to be improving quite a lot. So we have added ReLU activation, so looks like now it is actually applying non-linear, non-straight lines and straight lines. So this is a combination of straight and non-straight lines, and it is learning quite well. It has separated quite a blue dots from red dots in the train, and also in the test, red dots and blue dots are separated quite well. So our model has is moving in the right direction. So now let us again create another model, or shall we just leave it up to here? Okay, let us create another model. Let us add more hidden layers, more hidden units, and let us see if the accuracy can go more higher and the loss can go more down. So the aim is to exactly separate red dots and blue dots perfectly. So next, let us create another model, add more hidden units, more hidden layers, and see if it can separate blue dots and red dots more perfectly. So time for our next model. So let us create another model. I hope you're understanding the flow, right? At first, we created model 0. With model 0, we tried to separate red dots with blue dots using a straight line. And it was definitely not working very well. It was not able to separate red dots with blue dots. Then we created model 2. In model 2, we added more hidden layers and more hidden units, and visualized how our model was performing, and we found out that again it was not performing well. Then what we did was we created model 3 and we added new activation function, which is ReLU activation function. ReLU activation function gave our model chance to learn nonlinear patterns, and we can clearly see that our model was going in the right direction. It was separating blue dots with red dots. So what we want to do now is we want to create another improved version of model 3 where we want to add more hidden layers and more hidden units. So I hope you're understanding the flow. This is all experimentation, and this is what you'll actually do in the real world project as well. Not the exact toy data set, but you'll have a problem to work upon, and you will build subsequent models. First of all, you'll build base model, and then you will create models further, and then you'll see whether which model gives the correct output. So constructor has been created. We want to call the constructor of our superclass, which is another module init, and then we want, let's create layer 1 and then dot linear. Now what should be the in features? 2, because we have two features, x1 and x2. Now we want to increase the hidden units, so let us put 32. So hidden units are generally multiple of 8. Before we had 10 hidden units. This time we are adding more hidden units 32. Now let us create another layer 2, and then dot linear in features. So in features should match the out features of the previous layer. Out features 32. Let us create another layer 3, and then dot linear in features should be 32. Out features with 32, and another output layer 4, and then dot linear in features 32 and out features. So this is going to be our output layer, that's why the out features is 1. And ReLU layer, which really seems to be the key layer, key activation function for learning nonlinear patterns, or word function that we absolutely need to implement, otherwise it will result in error. So what we want to do, we want to pass our data through layer 1. From layer 1 it should go to layer 2, from layer 2 it should go to layer 3 and layer 4, but in between it should go through subsequent ReLU activation function. So it should go to layer 1. From layer 1 data should go to ReLU, then layer 2, then ReLU, then layer 3 to ReLU, and then final layer 4 should give what class it belongs to. So self dot layer 1 pass our data to layer 1, and then to self dot ReLU. From layer 1 it goes through ReLU activation, then it goes to layer 2. Again, from layer 2 it should go to ReLU activation. From ReLU activation it should go to again to layer 3 to learn linear pattern. Again from layer 3 it should go to self.ReLU, and finally our output layer, which is self.layer 4. So you see our data goes through so many layers. First of all, it goes through layer 1, it learns linear patterns, and it goes through ReLU activation where it learns non-linear patterns. Again it goes through layer 2 where it learns linear patterns. Again it goes through ReLU activation where it learns non-linear patterns, and so on. And finally it goes through layer 4 where layer 4 will tell how what class actually it belongs to. So let us run this cell, and now let us instantiate the model. So we want to name our model 4. We've already built ton of models. Circle B4, and again we want to send our model to target device. Also we want to send the model parameters to the target device. Next, model 4 dot parameters to the target device, and let us also let us visualize the random weight and bias that are initialized at the beginning. Model 4 dot parameters. Okay, this is a generated object, so we need to wrap it around list to visualize the model parameters. Okay, so we can see weights and biases of each layer. These are just random at the beginning. So now what we want to do is we want to create a training and evaluation loop, and then we want to change the weights and biases so that model can accurately predict which class it belongs to. In other words, it can perfectly separate red dots from blue dots. But before training and evaluation loop, we want to set up loss function. Again, we don't need to set up loss function each and every time because we've already set it at the beginning, but just for practice, let us set this optim.stochastic coordinate descent. It accepts parameters. In this time it's model 4 dot parameters, and learning rate, let's keep it 0.1. So now let us create our training and evaluation loop. Training and evaluation loop. So torch.manual seed 42 for reproducibility. And what we want to do is, for this time, let's train for 1500 iterations. Let's keep epoch as 1500. Again, device agnostic code. Our model is on target device, model parameter is on target device. The data that goes through the model should also be on target device. Xtrain, Ytrain, Xtrain to target device, Ytrain to the target device as well. Similarly, Xtest and Ytest should also be in the target device. I want you to practice as I am doing right now, because this is how you experiment and improve your model. You have to iterate some things, you have to try on different experimentation, and you want to change the hyperparameters, and then finally you will get a model that correctly suits your data and predicts accurately. So we want to iterate through each 1500 iterations. We want to go through 1500 iterations, epochs. So again, model 4 in training mode. Then we want to pass our Xtrain to the model. We want to squeeze it because we want to add an extra dimension. Model 4 will give losits. We want to change the logits to the format of zeros and ones. So what we will do is pass it through sigmoid activation, y logits, pass it through sigmoid activation, and then pass it, then round it. Then it will be in the format of 0 and 1. Let us store in the variable ypred. Let us calculate accuracy, our custom accuracy function invocation, and then what it accepts is y true is y train, and y prediction is y pred. Let us calculate the loss function. BC with logits loss expects logits, and then the actual value, which is y train. Now we want to do optimize zero grad, optimize zero grad, because gradients accumulate over each backward propagation, and we want to clear it. Now we want to do backward propagation. Again, we want to optimize a dot step, because we want to update the model parameters, weights and biases. So this was train loop. Now we want testing loop. Let us create a testing loop quickly. Model 4 into evaluation mode, because we want to turn off gradient tracking with torch.inference mode. So this makes our evaluation faster. Now what we want to do is model 4, and we want to pass, in our model 4 we want to pass x test, and we have to squeeze it because we want to add extra dimension. And then model 4 will give raw logits, which will store in y logits variable. We want to convert logits to something like 0 and 1. So torch.sigmoid test logits, and then we want to round it so that it is in the format of zeros and ones. And then let us store in the variable test spread. So test spread is in the format of zeros and ones. So now what we want to do is we want to calculate the accuracy. Let's create a new variable test accuracy, and then pass it through accuracy function. What our accuracy function expects, y true, which is y test, and y pred, which is test pred. Okay, so we also want to calculate loss, which we want to store in the variable test loss, and we want to invoke loss function. What we want to pass is test logits, because the loss function that we're using right now is BC with logits, and it expects logits, and the actual value is y test. So we want to, since we have 1500 iterations, let's have 15 output values, 15 print statements. So if epoch is exactly divisible by 100, then add a print statement, format epoch, the current epoch. We want to visualize train loss, and what we want is up to 5 decimal places. We want test train accuracy, and we want up to 2 decimal places. Also we want test loss, we want up to 5 decimal places, and test accuracy we want up to 2 decimal places. Test accuracy up to 2 decimal places. Now let us print this. We are printing loss. Yeah, let us run this cell, and let us visualize how our model is doing in training and evaluation. Okay, our model seems to be, the training loss seems to be going down, and the train accuracy also seems to be going up. Okay, the training accuracy is 100%, means out of 100 samples it predicted 100 correct. The test loss has also gone significantly down, and the test accuracy is 99.50. It is almost perfect. Out of 100 samples it predicts 99.50 correct. Wow, this is very good. Okay, let's visualize this. I'm excited for this. Let's copy this, paste. Let's see how our model is learning, how model separates red dots from blue dots in training and test. Oh my god, it is so perfect. Red dots and blue dots are separated perfectly in training, and in test, because the accuracy is 99%, this one red dot seems to be a bit in the blue side and in the red side, but other than that, every red dot and blue dots are separated. So our model 4 finally seems to be doing quite well. So you see how we built subsequent models, and finally our model 4 is doing so well. So this is what we've built. We've gone through subsequent models, we've created so many models, we've tried so many things. We changed the hidden units, hidden layers. We created another layer, ReLU layer, with a we created another model using ReLU activation. The model was able to learn nonlinear patterns. Then we found that the ReLU was the missing piece. Then we created another model, model 4, and then we added more hidden layer, more hidden units, and then finally our model is able to separate red dots with blue dots, and it perfectly separates each of this. So this was it for this video. I hope you understood multi-binary classification, where we separated, we imported make circles, we visualized the data, we created different models, and then finally we have a model which perfectly separates each of this. So if you like this video, please don't forget to subscribe, like, and comment, and let me know if you want more videos like this. The next video what I'll be uploading is multi-class classification. So this was binary classification. In binary classification, you separate red dots from blue dots, but in multi-class classification, rather than just blue and red dots, there can be more colors. So maybe you want to separate red, blue, yellow, green dots, so that will be more interesting. So that's it for this video. I hope you enjoyed. I hope you learned how to solve binary classification problem. See you in the next video. Please subscribe. Thank you.